A telescope just revealed something impossible. The universe we thought stretched 14 billion light-years actually spans 93 billion light-years across. The James Webb Telescope looked into a patch of empty sky and found 800,000 galaxies hiding in the darkness. Galaxies that formed when the cosmos was only 300 million years old. Black holes billions of times more massive than they should be. Structures stretching tens of millions of light-years when there wasn't enough time for them to grow. Everything we believed about the universe's size was wrong. If you're ready to see what's really out there, hit that like button and subscribe. We begin now. Light left this galaxy 280 million years after the Big Bang. It traveled through expanding space for over 13 billion years. Now, James Webb captured it. The galaxy's name is MOMZ-14, and astronomers confirmed its distance in 2025. This single discovery pushed our view of the universe back to a time when everything was still forming, still raw, still impossibly young. Here is what makes this insane. The universe is 13.8 billion years old today. MOMZ-14 existed when only 2% of that time had passed. Think about that ratio. If the universe's entire history was 1 year, this galaxy formed on January 7th. We are looking at cosmic infancy. The discovery happened because James Webb operates differently than older telescopes. It hunts for something called redshift. When light travels across billions of light-years, space itself expands. That expansion stretches the light waves, pulling them from visible colors into infrared radiation. The farther away something is, the more its light gets stretched. MOMZ-14 has a redshift value of 14.44. That number means extreme distance. It beat the previous record holder by just 10 million years, which sounds small, but in the early universe, everything changed fast. What shocks scientists is that MOMZ-14 is not a tiny speck. The galaxy is bright. It is actively forming stars during a burst of rapid creation. Nitrogen levels inside it mirror ancient star clusters we see in our own galaxy today, suggesting that star formation worked the same way even back then. This should not be possible according to older models. Galaxies were supposed to grow slowly, carefully, over hundreds of millions of years. MOMZ-14 shows us they did not. James Webb found it by combing through existing images looking for candidates. When astronomers spotted the faint signal, they turned the telescope back toward it in April 2025 for confirmation. The spectroscopy came back clear, confirmed. Not a theory, not a guess. Real data proving this galaxy existed at the edge of what we can observe. Here is the frightening part. MOMZ-14 is probably not the limit. The Nancy Grace Roman Space Telescope launches in 2027, designed to scan massive portions of sky at once. It will likely find galaxies even farther back. Each new discovery pushes the boundary closer to the Big Bang itself, and every time we push that boundary, we discover something that should not be there yet. Something forming too fast, shining too bright, existing too early. The universe had less than 300 million years to create MOMZ-14. 300 million sounds long, but in cosmic terms, it is a blink. For comparison, Earth has existed for 4.5 billion years. The dinosaurs walked around for 165 million years. MOMZ-14 assembled itself in less time than that. Stars formed, gas collapsed, structure emerged, all of it happening in the darkness of the infant cosmos. What we thought we knew about galaxy formation is crumbling, and this is just the beginning. James Webb does not see like you see. It cannot detect visible light. Instead, it captures infrared radiation, which is invisible to human eyes. This design choice is what makes the telescope so powerful for looking at the early universe. Without it, none of these discoveries would exist. When you look at a star, you see light that left it years ago. The star nearest to us beyond our own is over 4 light-years away. That means the light you see tonight left that star 4 years in the past. You are always looking backward in time when you look up. James Webb takes this principle to an extreme. It stares at objects so distant that their light has been traveling for over 13 billion years. The telescope is a time machine. Infrared vision matters because of expansion. The universe is not static. Space grows larger every second. As it grows, it stretches everything inside it, including light waves. Light that started as ultraviolet or visible radiation gets pulled into longer wavelengths. By the time it reaches us, it has shifted completely into infrared. Objects from the early universe become invisible to telescopes that only see visible light. The Hubble Space Telescope could not find galaxies like Mom-Z 14 because their light had redshifted beyond what Hubble could detect. James Webb sits at a location called Lagrange Point 2, about 930,000 miles from Earth. This position keeps it in permanent shadow from both Earth and our star, which is critical. Infrared sensors must be kept incredibly cold. If they heat up, they create their own infrared glow that drowns out the faint signals from distant galaxies. Webb's instruments operate at around -370 degrees Fahrenheit. That is colder than the surface of Pluto. The telescope's primary mirror spans 21 feet across. It is made of 18 hexagonal segments coated with gold. Gold reflects infrared light better than any other material. Each segment can be adjusted individually by tiny motors, allowing the entire mirror to focus perfectly. This precision means Webb can collect light from objects 100 times fainter than what Hubble could see. Here is how it finds early galaxies. Astronomers program Webb to observe specific patches of sky for hours or even days. The longer the telescope stares, the more faint light it gathers. Photons that left galaxies billions of years ago trickle in one by one. Webb's detectors count them. Over time, an image builds. Galaxies that would be invisible with a shorter observation become visible with patience. The spectrograph instruments then analyze the light. They split it into individual wavelengths, creating what scientists call a spectrum. Every element emits light at specific wavelengths, creating a unique fingerprint. Hydrogen looks different from helium. Oxygen looks different from carbon. By reading these fingerprints, Webb determines what a galaxy is made of, how fast it is moving, and most importantly, how far away it is. The redshift measurement comes from these spectra. It is the key to unlocking cosmic distance. What makes this terrifying is the scale. Every deep field image Webb takes reveals thousands of galaxies, and each one is a world we will never visit, a place so far away that we are seeing it as it was when the universe was a child. Close your eyes and picture nothingness. That is what the universe looked like for its first few 100 million years. Darkness everywhere. No stars yet. No galaxies. Just hydrogen and helium gas floating in the void, slowly clumping together under gravity's pull. This era is called the Cosmic Dark Ages, and it lasted longer than you would think. Then, something changed. Gravity won. The gas collapsed into dense pockets. Pressure built. Temperatures rose, and the first stars ignited. That moment ended the Dark Ages and began the cosmic dawn. Mom-Z 14 formed during this dawn, when light was just starting to flood the universe. 280 million years sounds like a long time. It is not. Not for building a galaxy. Think about the steps required. You need gas clouds to collapse. You need stars to form from that gas. You need those stars to cluster together. You need heavy elements to get created inside those stars, which takes multiple stellar generations. Each step requires time, yet Mom-Z 14 completed all of this in under 300 million years. Here is what the universe looked like back then. Space was smaller, much smaller. Everything was closer together. The average temperature was higher because all that matter was compressed into less volume. Radiation from the Big Bang still filled the cosmos, though it had cooled significantly. Dark matter halos were forming, creating gravitational wells where regular matter could gather. These halos acted like invisible scaffolding for the first galaxies. The gas itself was almost pure hydrogen and helium. No oxygen yet, no carbon, no nitrogen, none of the elements that make up planets or life. Those elements had to be forged inside stars first. When massive stars exploded as supernovas, they scattered heavier elements into space. The next generation of stars incorporated those elements. This process is called stellar nucleosynthesis, and it takes time, multiple cycles, multiple explosions. What confuses scientists is that MOMZ-14 already shows signs of nitrogen. That means at least 1 or 2 generations of stars had already lived and died inside this galaxy. In less than 300 million years, stars formed, burned through their fuel, exploded, enriched the gas around them, and allowed new stars to form with those enriched materials. The timeline is compressed almost impossibly tight. Compare this to our own galaxy. The Milky Way has existed for over 13 billion years. It has had time to go through countless cycles of star birth and death. It has had time to build up a rich inventory of heavy elements. Earth itself contains iron, silicon, gold, uranium, and dozens of other elements that did not exist when the universe was young. All of that material came from ancient supernovas. MOMZ-14 started that same process in a fraction of the time. And it is not alone. James Webb has found over 100 galaxies from this same early period, each one bright, each one actively forming stars, each one challenging the models that predicted galaxies should form slowly. The cosmic dawn was not gradual, it was an explosion of activity. Galaxies appeared fast, shining intensely, transforming the universe from darkness into light within a few 100 million years. And we are only now seeing the evidence, 13 billion years later, because light takes that long to reach us. What this tells us is unsettling. The universe does not follow the slow, careful progression we expected. It moves fast when it wants to, and the forces driving galaxy formation in the early universe were stronger than anything we see today. There is a black hole inside galaxy CANUCSLRDZ86. The galaxy existed 570 million years after the Big Bang. That alone is impressive. What makes it impossible is the black hole's size. It is supermassive, millions of times heavier than our star, and it is feeding rapidly, pulling in matter at a rate that breaks theoretical limits. Black holes form when massive stars collapse. A star 20 times heavier than ours can explode as a supernova, and its core implodes into a black hole weighing maybe 50 times what our star weighs. That is a stellar mass black hole. It is tiny compared to supermassive black holes, which weigh millions or billions of times more. How do you get from 50 to a million? You need time, lots of time. The black hole has to eat. It has to consume gas, dust, and other stars over hundreds of millions or billions of years. Here is the problem. CANUCSLRDZ86 did not have that time. The universe was barely 500 million years old when this galaxy existed. That is nowhere near enough time for a supermassive black hole to grow through normal feeding. Yet, there it is, confirmed by spectroscopy from James Webb. Not a theory, not speculation, real data. The galaxy belongs to a class called little red dots. These objects are small, faint, and extremely red because of their distance. James Webb has discovered dozens of them since operations began. Most confuse astronomers because they are either too dense with stars or they contain black holes too massive for their size. CANUCSLRDZ86 falls into the second category. The black hole outweighs the galaxy's stars by a significant margin. How did it get that big that fast? There are two main theories. First, the black hole could have formed from a massive gas cloud that collapsed directly without forming a star first. This would create what scientists call a heavy seed black hole, maybe thousands of times heavier than our star right from birth. That gives it a head start. The second theory involves supermassive stars. these hypothetical stars would be hundreds or thousands of times heavier than normal stars. When they collapsed, they would leave behind heavy black holes immediately. Both theories have problems. Direct collapse requires very specific conditions that may not have been common in the early universe. Supermassive stars are theoretical and have never been observed. Yet something created these black holes because we can see them now. The feeding rate makes it worse. James Webb detected gas swirling around the black hole at incredible speeds. The gas is highly ionized, meaning radiation from the black hole has stripped electrons from atoms. This is a signature of rapid accretion. The black hole is eating matter more than 40 times faster than the theoretical Eddington limit, which is the maximum rate a black hole should be able to feed before radiation pressure pushes away incoming matter. Think about that. Physics says there is a speed limit to how fast black holes can eat. This one is ignoring the limit. It is gorging itself, growing at a breakneck pace that should not be possible. If it keeps feeding at this rate, it will become a monster in relatively little time. What scares scientists is the implication. If CANUCSLRDZ86 is not unique, if there are thousands or millions of galaxies like it in the early universe, then supermassive black holes must have formed faster and more easily than we ever imagined. They did not take billions of years to grow. They appeared early, hungry, and ready to devour everything around them. The universe was wild in its youth, violent, fast, and every rule we thought governed black hole growth is being rewritten as James Webb keeps staring into the past. James Webb started finding them immediately, tiny red smudges scattered across deep field images. At first, astronomers thought they were just distant normal galaxies. Then the spectroscopy came back. These objects are not normal, not even close. They are compact, extremely luminous, and their properties make no sense according to standard models. Scientists call them little red dots, and they are rewriting the rules of early galaxy evolution. Over 100 of these objects have been identified so far. They all share common traits. First, they are small, much smaller than typical galaxies from the same era. Second, they are red because their light has been stretched by cosmic expansion. Third, they are bright, way too bright for their size. And fourth, they contain either extremely dense star clusters or massive black holes that should not fit inside them. Here is what makes them bizarre. If you calculate the mass of stars needed to produce their brightness, you get a number that is impossibly dense. The stars would be packed so tightly that they would collide and merge constantly. That does not happen in any galaxy we see today. Alternatively, if a supermassive black hole is producing the light, then the black hole is too big for the galaxy hosting it. In modern galaxies, black holes weigh about 0.1% of the galaxy's total mass. In little red dots, the black hole can weigh as much as the entire galaxy's stars combined. Both options break the models. Astronomers thought galaxies and their central black holes grew together, maintaining a balanced ratio. The galaxy forms first, building up stars over time. The black hole grows slower, feeding on gas that falls toward the center. Eventually, they reach equilibrium. Little red dots show this relationship inverted. The black hole got huge first, overpowering the galaxy around it. Another mystery is their abundance. Before James Webb, astronomers expected to find maybe a handful of unusual galaxies in the early universe. Instead, there are hundreds. They are not rare oddities. They are common. That means whatever process created them was not a fluke. It was a standard part of how the early universe worked. Some scientists think little red dots are transition objects. They might be catching galaxies in the middle of a growth spurt, when the central black hole is feeding rapidly, but the surrounding galaxy has not caught up yet. Over time, the galaxy might grow more stars and become a normal quasar, the bright objects powered by supermassive black holes that we see throughout the universe. If this is true, then little red dots are a snapshot of youth, a phase all galaxies go through before maturing. Others think they represent a completely different formation pathway. Maybe some galaxies form black holes first and build stars around them later. Maybe dark matter plays a bigger role than we realized. Maybe the early universe had conditions that allowed black holes to grow faster than they can today. One thing is certain: little red dots are not going away. Every new James Webb observation finds more of them. They appear at multiple distances, meaning they existed throughout the first billion years of the universe. They were not limited to one specific time period. They were everywhere. The most unsettling part is what they say about our models. We built equations to describe how galaxies form. We ran computer simulations to test those equations. The simulations predicted slow, steady growth. They predicted galaxies forming stars over billions of years. They predicted black holes staying small relative to their host galaxies. Little red dots break all three predictions. The universe was not patient in its youth. It was chaotic and fast and intense. Little red dots are the proof, scattered across the sky like cosmic mysteries waiting to be solved. Physics has limits. There are rules about how fast black holes can consume matter. These rules are not suggestions. They are consequences of radiation pressure and gravitational forces. A black hole named LID 568 is ignoring those rules completely, and astronomers have no idea how. The black hole sits at the center of a dwarf galaxy, visible as it existed 1.5 billion years after the Big Bang. James Webb and the Chandra X-ray Observatory both observed it. The data came back clear. LID 568 is feeding at over 40 times the Eddington limit. That limit is the theoretical maximum rate at which a black hole can pull in matter before its own radiation pushes that matter away. Here is how the limit works. When matter falls toward a black hole, it forms a swirling disk around the event horizon. Friction in this disk heats the matter to millions of degrees. Hot matter emits radiation, including intense X-rays. That radiation exerts pressure outward. If too much matter falls in too fast, the radiation pressure becomes strong enough to blow away the incoming material. The black hole essentially chokes itself, preventing faster feeding. This creates a natural speed limit. LID 568 is exceeding that limit by 40 times. 40, not 10% faster, not twice as fast, 40 times. That is like saying a car with a top speed of 100 miles per hour is somehow traveling at 4,000 miles per hour. The physics should not allow it. One possibility is super Eddington accretion. This happens when matter falls in from all directions simultaneously, overwhelming the radiation pressure through sheer volume. Imagine trying to stop a tidal wave with a fan. The wave wins. If enough gas collapses onto the black hole at once, the radiation cannot push it all away fast enough. The black hole gorges itself in a short, intense burst. These feeding frenzies are likely rare and short-lived. A black hole cannot sustain super Eddington accretion for millions of years. The surrounding gas supply would run out. What makes LID 568 important is that astronomers caught it during this brief phase. It is a snapshot of rapid growth, the kind of event that might explain how supermassive black holes got so big so fast in the early universe. The black hole's mass is relatively small for a supermassive black hole, only a few million times heavier than our star. That makes sense given how young the universe was when LID 568 formed. What does not make sense is how bright it is. The energy pouring out of the accretion disk is enormous. X-rays scream into space. The surrounding gas glows with heat. If this feeding rate continued for just a few million years, the black hole would double in size. Scientists think events like this might have been common in the early universe. Gas was denser back then. Galaxies were still forming, their structure chaotic and unstable. Massive gas clouds could collapse directly onto young black holes, triggering super Eddington feeding episodes. Each burst would add significant mass quickly. Over time, through multiple episodes, a black hole could grow from stellar mass to supermassive in far less time than normal accretion would allow. James Webb's discovery of LID 568 is critical because it provides evidence for this theory. Before this, super Eddington accretion was hypothetical. Now we have observed it. We have measured it. We know it happens. The question shifts from whether it is possible to how often it occurred. The universe is stranger than the equations suggest. Black holes do not always follow the limits we calculate. Under the right conditions, they break the rules. And in the early cosmos, those right conditions may have been everywhere. Imagine holding a grain of sand at arm's length and looking at the sky. The area that grain blocks contains almost 800,000 galaxies. That is what the Cosmos Webb survey revealed after James Webb spent over 200 hours staring at one patch of space. The survey covered 0.6 square degrees of sky. For reference, the full moon covers about 0.2 square degrees, so we are talking about an area roughly 3 times the size of the full moon. In cosmic terms, this is microscopic, a tiny sliver. Yet within that sliver, James Webb found more galaxies than most people can comprehend. 800,000 galaxies, each one containing billions or trillions of stars. Each one existing at different distances, meaning different times in the universe's history. Some are nearby, showing us galaxies as they look relatively recently. Others are so distant their light left them over 13 billion years ago. The survey essentially created a timeline of cosmic history, all visible in one image. The Cosmos Webb project used James Webb's near-infrared camera and mid-infrared instrument to capture the data. Astronomers chose the Cosmos field specifically because it has very few foreground stars or gas clouds blocking the view. This gives a clear line of sight deep into space. The field has been observed by multiple telescopes over the years, including Hubble, but James Webb's infrared sensitivity allowed it to see galaxies Hubble missed entirely. What makes this survey revolutionary is its combination of width and depth. Many deep field images focus on extremely small areas, maximizing the observation time to see the faintest objects possible. Cosmos Webb sacrificed some depth to cover a larger area, revealing how galaxies are distributed across space. The result is a map showing galactic structures, clusters, and voids spanning billions of light years. The image shows galaxies at every stage of evolution: spiral galaxies with elegant arms, elliptical galaxies that are smooth and featureless, irregular galaxies twisted by gravitational interactions, galaxies in the process of merging, their structures distorted as they collide, and everywhere, little red dots from the early universe, scattered like embers from the cosmic dawn. One unexpected finding is the sheer number of early galaxies. Before James Webb, models predicted far fewer bright galaxies in the first billion years after the Big Bang. The Cosmos Webb survey found 10 times more than expected. This suggests galaxy formation was more efficient and happened faster than theories predicted. The early universe was not empty and quiet. It was crowded and active. The survey also revealed structures forming earlier than anticipated. Galaxy groups and clusters that should have taken longer to assemble are already visible in the early universe. Gravity pulled galaxies together faster than models suggested. The cosmic web, the large-scale structure of the universe with its filaments and voids, was already taking shape when the universe was just a few billion years old. Each galaxy in the image has a story, each one formed through a unique combination of dark matter, gas collapse, and star formation. Some experienced violent mergers, some grew quietly over billions of years. Some are actively forming stars right now, their light showing the glow of young, hot, stellar populations. Others are old and dead, their stars long since burned out, their light a ghostly echo of past activity. The Cosmos Webb survey will be studied for years. Astronomers will analyze individual galaxies, measure their distances, study their compositions, and track how they change over time. Every new analysis will refine our understanding of cosmic evolution. Every discovery will add another piece to the puzzle of how the universe grew from the Big Bang's fireball into the structured cosmos we see today. And this is just one patch of sky. There are over 40,000 square degrees across the entire celestial sphere. If every patch contains this many galaxies, the total number in the observable universe exceeds 2 trillion. That number is so large, it loses meaning. We cannot visualize 2 trillion. We can only understand it as a symbol of the universe's incomprehensible vastness. A black hole is moving through space at 2 million miles per hour. It is not orbiting anything. It is not falling toward anything. It is running, fleeing, and it is dragging a trail of newborn stars behind it like a cosmic scar 200,000 light-years long. The black hole weighs 10 million times what our star weighs. That is supermassive by any measure. Yet something kicked it out of its home galaxy with enough force to send it rocketing through space at 3,000 times the speed of sound. James Webb confirmed this discovery in 2025, and astronomers are calling it the first verified runaway supermassive black hole. The object sits in the Cosmic Owl galaxy system, which is actually multiple galaxies in the process of merging. When galaxies collide, their central black holes eventually sink toward the merged galaxy's center. Usually. In rare cases, gravitational interactions can eject one of the black holes entirely. That is what happened here. There are 2 ways to kick out a black hole this massive. First, when 2 supermassive black holes merge, they release gravitational waves. These waves carry momentum, and if they are emitted asymmetrically, they can give the resulting merged black hole a powerful kick. Think of it like recoil from a gun. The black hole gets pushed in one direction at high speed. Velocities can reach thousands of miles per second, more than enough to escape the galaxy's gravity. The second method involves 3 black holes. If a galaxy already had a binary pair of black holes at its center, and a third black hole entered the system during a merger, the interaction becomes unstable. One of the 3 gets slingshot out. This is a 3-body problem, the kind of chaotic gravitational dance that has no stable solution. One black hole always loses and gets ejected. James Webb observed the black hole by detecting a bow shock in front of it. As the black hole plows through intergalactic gas at tremendous speed, it compresses the gas ahead of it, creating a shock wave like a boat moving through water. That shocked gas heats up and glows. The telescope also detected the trail behind the black hole, a long filament where gas is collapsing and forming stars. The black hole's passage triggered star formation along its entire path. This is unprecedented. Stars forming in the wake of a runaway black hole. The gas gets compressed by the black hole's gravity as it passes, and that compression causes collapse. New stars ignite behind the fleeing giant. The trail is visible because young stars are bright. They shine in ultraviolet and visible light, and their light gets redshifted into infrared by the time it reaches us. The speed is mind-boggling, 2 million miles per hour. In 1 second, this black hole travels over 500 miles. It crosses the distance from Earth to our moon in less than 2 minutes. At this rate, it will escape the Cosmic Owl system entirely and wander through intergalactic space as a rogue object. Galaxies without central black holes are rare, but this one is about to become homeless. What does this mean for our understanding of black hole evolution? Runaway black holes were predicted by simulations, but finding one confirms they exist. It also raises questions about how common they are. If galaxy mergers frequently eject black holes, there could be thousands of rogues drifting through space, invisible because they are no longer feeding on matter. The discovery also suggests black hole mergers in the early universe may have been chaotic. As galaxies formed and collided during the cosmic dawn, their black holes would have interacted violently. Some merged, some got ejected. The process was messy, unpredictable, and resulted in black holes scattered across the cosmos. James Webb's ability to detect this object shows how sensitive the telescope is to faint structures. The bow shock and star trail are not bright. They required long exposure times and careful analysis to identify. Yet, they revealed something no one had seen before: a supermassive black hole in full retreat, racing away from home and leaving a trail of creation in its wake. Two black holes are colliding inside galaxy system ZS7. The system existed 740 million years after the Big Bang. Both black holes are supermassive, each weighing millions of times what our star weighs. They are circling each other, spiraling inward, and they will eventually merge into one even larger black hole. When that happens, the collision will shake space-time itself. James Webb detected the merger by analyzing the spectrum of light from ZS7. The data showed two distinct sources of energetic radiation very close together. Both sources displayed the signatures of accreting black holes, fast-moving gas, intense ionization, and broad emission lines, from atoms swirling at incredible velocities. The two sources are separated by only a few thousand light-years, and they are moving toward each other. This is the most distant black hole merger ever detected. It is also the earliest in cosmic time. Previous mergers have been observed in the modern universe, but never this far back. The discovery confirms that black holes were already colliding and merging when the universe was less than 1 billion years old. This has major implications for how supermassive black holes grew so large so quickly. Mergers are one of the fastest ways to build massive black holes. Instead of slowly accreting gas over millions of years, two black holes can combine their mass in a single event. If mergers were common in the early universe, they could explain how supermassive black holes reached billions of solar masses within the first billion years after the Big Bang. The merger process itself is fascinating. As two black holes orbit each other, they emit gravitational waves. These are ripples in space-time predicted by Einstein's general relativity. The waves carry energy away from the system, causing the orbits to decay. The black holes spiral closer and closer, moving faster and faster until they collide. The final merger happens in a fraction of a second, releasing more energy than all the stars in the visible universe combined. We cannot detect the gravitational waves from ZS7 with current technology. The waves are too faint after traveling over 13 billion light-years. However, future observatories will be able to. The Laser Interferometer Space Antenna, scheduled to launch in the 2030s, is designed specifically to detect gravitational waves from supermassive black hole mergers. When it becomes operational, it will observe events like ZS7 routinely. What makes this discovery critical is that it provides a preview of what LISA will detect. Before James Webb found mergers in the early universe, scientists thought events like ZS7 would be rare. Now they know mergers were common. That means LISA will detect far more gravitational wave events than initially predicted. The rate of black hole mergers in the infant universe was much higher than models suggested. The merger also tells us about galaxy evolution. ZS7 is formed from two galaxies colliding and combining. As the galaxies merge, their black holes sink toward the center of the new combined galaxy. This process is called dynamical friction. The black holes interact with stars and gas, losing energy and spiraling inward. Eventually, they form a binary pair, which then merges. This sequence happens throughout cosmic history. Galaxies collide constantly. The Milky Way is currently on a collision course with the Andromeda Galaxy, and they will merge in about 4 billion years. When they do, their central black holes will eventually merge as well. The process we see in ZS7 is the same process that will happen to our own galaxy in the distant future. The gravitational waves from the ZS7 merger were emitted 13 billion years ago. They have been traveling through space ever since, stretching as the universe expanded. By the time LISA detects them, they will have been transformed into long wavelength signals that require space-based detectors to observe. Those waves carry information about the masses of the black holes, their spins, and the dynamics of the merger. Future astronomers will decode that information to learn details James Webb cannot see. There is a galaxy named JADESGSZ140. It existed 290 million years after the Big Bang. James Webb measured its brightness and determined it is forming stars at an absurd rate. The galaxy is creating new stellar mass 100 times faster than models predicted possible for its age. Star formation requires gas. Hydrogen clouds collapse under gravity, compressing until temperatures reach 10 million degrees. At that point, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing energy. A star is born. The process takes millions of years from start to finish, and it requires specific conditions. The gas must be dense enough. It must be cool enough. Turbulence must not disrupt the collapse. In the modern universe, galaxies form stars relatively slowly. The Milky Way creates about 3 new stars per year. That sounds fast, but our galaxy contains hundreds of billions of existing stars. The star formation rate is low compared to the total stellar mass. This is typical for mature galaxies. Most of their gas has already been converted into stars or expelled by stellar winds and supernovas. JADESGSZ140 is different. It is forming stars at a rate that would create the mass equivalent of hundreds or thousands of stars per year. For a galaxy that young and small, that rate is extreme. It means the entire galaxy is a star-forming furnace, with gas clouds collapsing simultaneously across its entire volume. Why is this happening? One theory involves cold streams of gas falling onto the galaxy from surrounding space. In the early universe, gas was distributed differently than today. Dark matter halos acted as gravitational wells, pulling in gas from vast distances. That gas flowed along filaments, streaming into young galaxies like rivers feeding a lake. The influx provided a constant supply of raw material for star formation. Another possibility is that the galaxy recently experienced a merger. When 2 galaxies collide, their gas clouds smash together, triggering massive bursts of star formation. The collision compresses the gas, causing widespread collapse. Star formation rates can spike by factors of 10 or more during these events. JADESGSZ140 might be caught in the middle of such a burst. The brightness is another mystery. Young stars are hot and luminous. They emit tremendous amounts of ultraviolet light. That light heats surrounding gas, causing it to glow. The combination makes the galaxy shine brightly. However, JADESGSZ140 is brighter than expected, even accounting for its star formation rate. The light output suggests either the stars are unusually massive or there is another energy source contributing to the glow. Some astronomers think supermassive stars might be involved. These hypothetical objects would weigh hundreds of times more than typical stars. They would burn incredibly hot and bright, living only a few million years before exploding. If JADESGSZ140 formed a population of supermassive stars, their combined light would explain the excessive brightness. However, supermassive stars remain theoretical. No confirmed observations exist. The galaxy's spectrum shows strong emission lines from oxygen and hydrogen. This confirms active star formation. The lines are broader than expected, suggesting the gas is turbulent and moving at high speeds. This turbulence might be driven by stellar winds and supernova explosions. Young, massive stars die quickly and violently, injecting energy into their surroundings. That energy stirs up the gas, creating chaotic motion. What bothers scientists is the short timescale. At 290 million years after the Big Bang, the universe barely had time to form the first generation of stars, let alone build a massive star-forming galaxy. JADESGSZ140 should be in its infancy, just beginning to assemble. Instead, it is fully active, producing stars at a breakneck pace. This suggests galaxy formation was more efficient in the early universe than current models predict. Gas collapsed faster. Stars formed quicker. feedback mechanisms that slow star formation in modern galaxies were weaker or absent. The early cosmos was a more productive environment for building galaxies. Every discovery, like JADESGSZ140, forces astronomers to revise their models. The numbers get adjusted, the timelines get compressed, and the picture of the early universe becomes more chaotic, more violent, and more impressive than we ever imagined. The universe is expanding. We have known this since the 1920s. What we do not know is exactly how fast it is expanding. Two different methods give two different answers, and the discrepancy is big enough that it cannot be ignored. Astronomers call this the Hubble tension, and James Webb just confirmed it is real. The expansion rate is measured by a number called the Hubble constant. It tells us how fast galaxies are moving away from us at a given distance. If the Hubble constant is 70, that means a galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. The farther away something is, the faster it moves away. There are two main ways to measure this constant. The first uses observations of the cosmic microwave background, the faint glow left over from the Big Bang. This radiation fills the entire universe and carries information about the cosmos as it existed 380,000 years after the Big Bang. By analyzing tiny temperature variations in this radiation, scientists can calculate how fast the universe was expanding back then. They then use models to project forward to the present day. This method gives a Hubble constant of about 67. The second method uses nearby stars and galaxies. Astronomers measure the distance to galaxies using objects called Cepheid variable stars and type Ia supernovas. Both are well understood and can be used as distance markers. By measuring how fast these galaxies are moving away from us and comparing that to their distance, scientists calculate the Hubble constant directly. This method gives a value of about 73. 6 points is a huge difference. It is not a rounding error. It is not measurement uncertainty. Both methods are precise and have been checked repeatedly. The discrepancy is real, and it has persisted for over a decade. This is the Hubble tension. James Webb's role in this mystery is critical. One concern was that Hubble Space Telescope measurements might have errors. Maybe the distances were wrong. Maybe something about how Hubble observed Cepheid stars introduced a systematic bias. James Webb can observe the same stars with better sensitivity and resolution. If Hubble's measurements were flawed, Webb would find different values. Webb did not find different values. It confirmed Hubble's measurements. The distances are correct. The expansion rate is really about 73 when measured using nearby objects. The tension is not due to observational error. It is real. This leaves two possibilities. Either our model of the universe is incomplete, or something changed in how the universe expands over time. The standard model of cosmology assumes the expansion rate follows a smooth, predictable pattern determined by the amounts of matter, and dark energy in the universe. If those assumptions are wrong, the model breaks down. One idea is that dark energy behaves differently than we think. Dark energy is the mysterious force causing the universe's expansion to accelerate. It makes up about 68% of the universe's total energy. We do not know what it is, only that it exists. If dark energy's strength changed over cosmic history, that could explain the tension. The early universe might have expanded at one rate, while the current universe expands at a different rate. Another possibility is that there is an unknown component to the universe we have not detected yet. Some new form of energy or matter that affects expansion. This would be a major discovery, equivalent to finding a missing ingredient in the recipe for the cosmos. Or maybe the problem is with the cosmic microwave background analysis. Perhaps the models used to interpret that data are flawed. If the early universe was different than we assume, the projections to the present day would be wrong. The Hubble tension is one of the biggest puzzles in modern cosmology. It suggests our understanding of the universe is incomplete. Something is missing, something we have not accounted for. And until we figure out what that something is, the tension will remain, a crack in the foundation of our cosmic models. There is a galaxy called LAP 1b. James Webb observed it as part of a survey looking for unusual objects in the early universe. The spectrum came back strange. No oxygen, no carbon, almost nothing except hydrogen and helium. This might be the signature of population. 3 stars, the very first stars to ever form. Stars are divided into populations based on their metal content. In astronomy, metals mean anything heavier than helium. Iron is a metal, carbon is a metal, oxygen is a metal. Modern stars contain a few percent metals by mass. These are called population 1 stars. Older stars contain less metal, maybe 1/10 of 1%. These are population 2 stars. Population 3 stars would have 0 metals formed from the pure hydrogen and helium that existed right after the Big Bang. No one has ever confirmed a population 3 star. They should have existed, but they died billions of years ago. These stars would have been massive, burning through their fuel in just a few million years before exploding as supernovas. Those explosions scattered the first heavy elements into space, seeding the universe with materials for the next generation. Every star we see today, including our own, contains metals forged by population 3 stars. Finding them is hard because they are so old. Any population, 3 stars still shining, would be in the most distant galaxies, visible only as they existed in the early universe. Their light would be faint and red-shifted. Even James Webb struggles to detect individual stars at such distances. Instead, astronomers look for galaxies where population 3 stars might still dominate the stellar population. LAP-1b is a candidate. The galaxy's spectrum shows almost no metal lines. The light is dominated by hydrogen and helium emission. This could mean the galaxy contains mostly population 3 stars, though other explanations are possible. The galaxy might just have very pristine gas that has not been enriched by supernovas yet, or the spectrum might be showing gas clouds rather than stars. Confirming population 3 stars requires deeper observations. James Webb needs to look longer, gathering more photons to detect fainter spectral features. If oxygen is completely absent, that would strengthen the case. Population 3 stars do not produce much oxygen because they explode before forming it. Later, stellar generations create oxygen through fusion in their cores and release it when they explode. Why does this matter? Population 3 stars shaped the universe. They were the first sources of light after the cosmic dark ages. Their ultraviolet radiation ionized the surrounding hydrogen, transforming neutral gas into plasma. This process is called reionization, and it fundamentally changed the universe's structure. Without population 3 stars, reionization would not have happened, and the universe would look completely different. These stars also set the stage for all future star formation. By creating the first heavy elements, they made planets possible. Carbon, oxygen, silicon, iron, all the materials that make up Earth came from supernovas of massive stars. Population 3 stars started that process. They were the cosmic alchemists, turning simple hydrogen and helium into the complex periodic table we rely on. Their masses are debated. Some models suggest they were hundreds of times heavier than our star. Others think they ranged from 10 to 100 times heavier. The difference matters because it affects how they exploded and what elements they produced. Very massive stars might have collapsed directly into black holes without exploding at all. If that happened, they would not have enriched the universe with metals, delaying the formation of later stellar generations. James Webb's discovery of LAP-1b offers a glimpse of what the earliest stars might have looked like. Even if this galaxy turns out not to contain population 3 stars, it shows that James Webb can detect objects pristine enough to be candidates. The telescope will continue surveying the early universe, and eventually, astronomers will find definitive proof of these ancient giants. When that happens, it will complete the story of stellar evolution. We will have observed stars from every era, from the first generation to the current one. We will understand how stars changed the universe from a simple cloud of hydrogen and helium into the rich, complex cosmos we inhabit today. James Webb keeps finding massive galaxies in the first billion years after the Big Bang. These are not small dwarf galaxies just forming their first stars. They are large, well-developed systems containing billions of stars. They should not exist yet. The universe did not have enough time to build them. Galaxy formation is supposed to be a gradual process. Dark matter halos form first, creating gravitational wells. Gas falls into those wells, accumulating over tens or hundreds of millions of years. Eventually, enough gas collects to start forming stars. The galaxy grows slowly, adding more mass over time through continuous star formation and mergers with smaller galaxies. Reaching a mass equivalent to tens of billions of stars should take at least 1 billion years. Yet James Webb found galaxies with exactly that mass at redshifts of 9, 10, even 11. These galaxies existed when the universe was less than 500 million years old. Some appear as early as 300 million years after the Big Bang. Their mere existence challenges the timeline. One example is a galaxy observed at redshift 11. The data shows it contains 10 billion times the mass of our star in the form of stars and gas. This is not a small galaxy. It is comparable in mass to the Large Magellanic Cloud, one of the Milky Way's satellite galaxies. The problem is the age. At redshift 11, the universe was only 400 million years old. Building 10 billion stellar masses in that time requires star formation rates far higher than models predict. The galaxies are not just massive, they are also mature. Their spectra show signs of older stellar populations, meaning the stars have been around for a while. Some galaxies even show evidence of dust, which forms from supernova ejecta. Dust takes time to accumulate. Its presence suggests the galaxy has already gone through multiple cycles of star formation and death. How did they grow so fast? One idea involves extremely efficient star formation. Maybe the first galaxies converted gas into stars at rates 10 or 20 times higher than modern galaxies. If star formation was that efficient, galaxies could reach large masses quickly. However, this requires explaining why efficiency was so high. What conditions in the early universe made star formation so effective? Another possibility is that dark matter halos grew faster than current models suggest. If halos assembled more quickly, they would pull in gas faster, accelerating galaxy growth. This could happen if dark matter has properties we have not accounted for, or if the early universe's density fluctuations were stronger than we realized. Mergers might also play a role. If small galaxies formed very early and merged rapidly, they could combine their masses into larger systems in less time. However, mergers alone probably cannot explain the most massive galaxies. The merger rate would need to be incredibly high, and there is not enough time for that many mergers to occur. Some scientists think the observations might be misinterpreted. The masses could be overestimated if the galaxies contain very bright stars or active black holes that mimic the light of many stars. If that is true, the actual stellar mass would be lower, making the galaxies less problematic. However, spectroscopy generally rules this out. The light from stars has a different signature than light from black holes, and most of these galaxies show stellar-dominated spectra. The discovery of massive early galaxies is forcing a rethink of galaxy formation models. The equations that describe how structure forms in the universe might need adjustment. The parameters that control star formation might need changing. Or there might be entirely new physics at play, something we have not considered because we never had observations this deep into the early universe. Every massive galaxy James Webb finds adds to the puzzle. Each one pushes the boundaries of what should be possible, and each one suggests the universe was more dynamic, more active, and more capable of rapid growth than we ever imagined. Hold a grain of sand at arm's length toward the night sky. The area it covers contains over 10,000 galaxies. That is not an exaggeration. That is what James Webb's first deep-field image revealed when it stared at galaxy cluster SMACS 0723 for 12.5 hours. The image covers a patch of sky so small you could block it with a pinhead. Yet within that tiny slice, the universe reveals its true scale. Galaxies crowd the frame, overlapping and intermingling. Some are bright spirals with clear structure. Others are faint smudges barely visible against the black background. A few are so distant their light has traveled for over 13 billion years to reach the telescope. The galaxy cluster, SMACS 0723, sits about 4 billion light-years away. The cluster itself is massive, containing hundreds of galaxies bound together by gravity. The combined mass of all those galaxies warps space-time around them, creating a gravitational lens. This lens bends and magnifies the light from galaxies far behind the cluster, allowing James Webb to see objects that would otherwise be too faint to detect. Gravitational lensing is one of the universe's natural tricks for revealing distant objects. Einstein predicted it in his general relativity equations. Massive objects curve space-time, and light traveling through curved spacetime follows a bent path. The result is similar to how a glass lens bends light to form an image. The galaxy cluster acts as a cosmic magnifying glass, bringing distant galaxies into view. Some of the galaxies in the image appear stretched and distorted, smeared into long arcs by the lensing effect. These arcs are actually single galaxies whose light has been bent around the cluster. By analyzing the distortion, astronomers can calculate the galaxy's distance and mass. The more distorted the image, the more massive the cluster and the farther away the background galaxy. The faintest objects in the image are also the oldest. Their light left them when the universe was less than 1 billion years old. These galaxies appear red because their light has been stretched by cosmic expansion. What was originally ultraviolet radiation has shifted into infrared wavelengths. James Webb's sensors are tuned to detect exactly this kind of light, making it perfect for finding the universe's most ancient structures. Each galaxy in the image has its own history. Some are young and actively forming stars. Others are old and dying, their stellar populations fading. Some have experienced mergers that twisted their shapes. Others grew in isolation, undisturbed for billions of years. The diversity is staggering. No two galaxies are identical. The deep field also shows the large-scale structure of the universe. Galaxies are not distributed randomly. They cluster together in groups and chains, forming a cosmic web. The web's filaments stretch across hundreds of millions of light-years, with vast empty voids in between. The SMACS 0723 cluster sits at a node in this web, a point where multiple filaments intersect. James Webb captured this image in 12.5 hours. The Hubble Space Telescope needed weeks to achieve similar depth. This improvement in efficiency means James Webb can survey larger areas of sky in less time, discovering more galaxies and building a more complete picture of cosmic history. The image is just the beginning. Astronomers will spend years analyzing it, measuring the properties of individual galaxies, calculating distances, and studying how galaxy populations change over time. Every galaxy offers clues about star formation, chemical enrichment, and the processes that drive cosmic evolution. What makes this image profound is the reminder it provides about scale. That tiny patch of sky contains thousands of galaxies. The entire sky contains over 40,000 square degrees. If every area has similar galaxy density, the observable universe contains trillions of galaxies. Trillions. Each one potentially containing billions of planets. Each one a universe unto itself, filled with stars and worlds and mysteries we will never reach. The grain of sand is a metaphor, but it is also a reality. The universe's vastness is incomprehensible. We can capture it in images. We can measure it with numbers, but we cannot truly grasp it. the mind fails to hold something so large. All we can do is marvel at the images and recognize how small our corner of existence really is. Light does not travel in straight lines near massive objects. It follows the curvature of space-time, bending around concentrations of mass. This bending is gravitational lensing, and it turns galaxy clusters into natural telescopes that reveal the universe's most distant structures. Galaxy clusters contain thousands of galaxies, each contributing mass. Dark matter, which outweighs visible matter by 5 to 1, adds even more mass without being seen. The combined gravitational field is enormous, warping space-time across millions of light-years. When light from a distant galaxy passes near the cluster, it gets deflected, often in multiple directions. The result is that a single background galaxy can produce multiple images. The light takes different paths around the cluster, arriving at our telescopes from slightly different angles. Each path creates a separate image. Sometimes these images appear as arcs or rings surrounding the cluster. Other times, they look like disconnected fragments scattered across the sky. By measuring the positions and shapes of these images, astronomers can reconstruct what the original galaxy looked like and calculate its distance. Gravitational lensing also magnifies light. The bending effect concentrates photons, making the background galaxy appear brighter than it would without the lens. This magnification can be significant, sometimes boosting a galaxy's brightness by factors of 10 or more. Galaxies that would be too faint for James Webb to detect become visible thanks to the lensing effect. One famous example is the cosmic horseshoe, a nearly complete ring formed by a distant galaxy lensed by a foreground galaxy cluster. The ring is not a physical structure. It is a trick of light, the image of a single galaxy stretched and wrapped around the cluster's gravitational field. Without lensing, this galaxy would appear as a tiny, faint smudge. With lensing, it becomes a spectacular arc visible across the sky. James Webb uses gravitational lensing to push its observations deeper than would otherwise be possible. By targeting galaxy clusters known to produce strong lensing effects, the telescope can see galaxies from the first few 100 million years after the Big Bang. These galaxies are so distant and faint that they would be invisible without the magnification provided by the clusters. One challenge with lensing is that it distorts the image. The galaxy's shape gets stretched, twisted, and fragmented. Reconstructing the original appearance requires sophisticated models that account for the cluster's mass distribution. Astronomers map the cluster's gravitational field by analyzing how it lenses multiple background galaxies. Once they know the field's shape, they can reverse the lensing effect and determine what the galaxies really look like. Another benefit of gravitational lensing is that it probes dark matter. The lensing strength depends on the total mass along the line of sight, including dark matter. By measuring the lensing effect, astronomers can map where dark matter is located in the cluster. These maps reveal that dark matter forms dense concentrations at the cluster's center, surrounded by more diffuse halos extending far beyond the visible galaxies. Sometimes gravitational lensing creates a rare phenomenon called an Einstein ring. This happens when a background galaxy, the lensing object, and the observer are perfectly aligned. The light from the background galaxy gets bent equally in all directions, forming a complete ring around the lensing object. Einstein rings are beautiful and symmetrical, but they are also scientifically valuable. The ring's radius depends on the lensing mass, providing a precise measurement of the cluster's weight. The most powerful lenses in the universe are galaxy clusters in the process of merging. When two clusters collide, their combined mass creates an even stronger gravitational field. These mergers produce extreme lensing effects that can magnify background galaxies by factors of 50 or more. James Webb has observed several merging clusters, revealing galaxies that would be impossible to see any other way. Gravitational lensing is one of the few tools that allows astronomers to study the universe's earliest galaxies in detail. Without it, objects from the cosmic dawn would remain invisible, too faint and too distant for even the most powerful telescopes to detect. The universe has provided us with natural magnifying glasses scattered across the sky, and James Webb is using them to peer deeper into time than ever before. A galaxy named Virgil looked ordinary in visible and ultraviolet light, young, quiet, forming stars at a modest rate. Then James Webb observed it in infrared. The galaxy transformed. At its center sat a massive, heavily obscured supermassive black hole pouring out enormous amounts of energy. The black hole was invisible in normal light because of dust. Thick clouds of dust surrounded the black hole, absorbing its ultraviolet and visible radiation. The dust heated up and re-emitted the energy as infrared light, which James Webb's instruments are designed to detect. This is why the telescope can see things other observatories miss. It looks where others cannot. Virgil is not alone. James Webb has discovered several galaxies with hidden supermassive black holes. These objects appear calm and unremarkable when observed in visible light, but infrared observations reveal intense activity at their cores. The black holes are feeding rapidly, pulling in gas and dust, but the surrounding material blocks the light from escaping in visible wavelengths. This discovery has major implications for understanding black hole demographics. Previous surveys that relied on visible and ultraviolet light may have missed a significant fraction of active black holes. If many black holes are hidden behind dust, then the total number of actively feeding supermassive black holes in the universe is higher than we thought. Why are these black holes so dusty? One reason is that they are still growing. Young galaxies contain more gas and dust than older galaxies. The material that feeds the black hole also obscures it. As the black hole accretes matter, the surrounding disk heats up and emits light, but before that light escapes, it hits dust particles orbiting farther out. The dust absorbs the light and glows in infrared. Another factor is geometry. If the dusty disk around the black hole is viewed edge-on, the dust blocks our view of the center. We see the galaxy's stars and gas, but the black hole itself is hidden. Only by observing in infrared, which penetrates dust more easily than visible light, can we detect the black hole's presence. Virgil's black hole is described as overmassive. The black hole's weight is higher than expected for a galaxy of Virgil's size. In most galaxies, the central black hole weighs about 0.1% of the galaxy's total stellar mass. In Virgil, the ratio is much higher. The black hole is disproportionately large, suggesting it grew faster than the surrounding galaxy. This raises questions about which comes first, the galaxy or the black hole. Traditional models assume galaxies form first, and black holes grow inside them. Virgil suggests the opposite might sometimes be true. Maybe the black hole forms early and grows rapidly, and the galaxy builds up around it over time. If this happens, we would expect to find galaxies like Virgil, where the black hole dominates the mass. The discovery also highlights the importance of multi-wavelength observations. Looking at objects in only one type of light gives an incomplete picture. Virgil appeared one way in visible light and completely different in infrared. To understand the full story, astronomers need data across the electromagnetic spectrum, from radio waves to gamma rays. James Webb's mid-infrared instrument was critical for revealing Virgil's hidden black hole. This instrument operates at wavelengths between 5 and 28 micrometers, well beyond what visible light telescopes can see. At these wavelengths, dust becomes transparent, and the heat from buried black holes becomes visible. How many more hidden black holes are out there? No one knows yet. James Webb has surveyed only a tiny fraction of the sky. As it continues observations, more galaxies like Virgil will likely be found. Each discovery adds to our understanding of how black holes and galaxies evolve together. The universe is full of secrets, and many are hidden behind veils of dust. James Webb is pulling back those veils one by one, revealing the structures and processes that shape cosmic evolution. What we thought we knew about galaxies is changing. The old picture, based on visible light alone, is incomplete. The new picture, enriched by infrared observations, is stranger and more complex than we imagined. James Webb found a problem. Early galaxies are too bright, not just a little brighter than predicted, but 10 times brighter. This is not a minor discrepancy. It means something fundamental is wrong with the models that describe how galaxies form and evolve in the first billion years after the Big Bang. The models are sophisticated. They incorporate dark matter, gas dynamics, star formation, and feedback from supernovas and black holes. Cosmologists run these models on supercomputers, simulating billions of years of cosmic history. The simulations predict how many galaxies should exist at different times and how bright those galaxies should be. Before James Webb, the predictions matched observations reasonably well. Hubble found galaxies in the early universe, and their numbers and brightness aligned with expectations. Then James Webb looked deeper, and the picture changed. The telescope revealed galaxies everywhere, far more numerous and luminous than the simulations predicted. What makes early galaxies so bright? One possibility is star formation efficiency. Maybe the first galaxies converted gas into stars more efficiently than modern galaxies. If every gas cloud that collapsed formed stars, instead of being disrupted by turbulence or feedback, the galaxy would produce more stars in less time. More stars mean more light. Another possibility involves the types of stars being formed. If early galaxies produced a higher proportion of massive stars, they would be brighter. Massive stars shine far more intensely than smaller stars. A star 100 times heavier than ours can be 1 million times brighter. If the stellar mass function in early galaxies was skewed toward heavy stars, the total luminosity would increase dramatically. Supermassive stars could also contribute. These hypothetical objects would be hundreds or thousands of times heavier than typical stars. They would shine with the light of entire galaxies, dominating the total luminosity. If even a small fraction of stars in early galaxies were supermassive, they would explain the excess brightness. However, supermassive stars are theoretical and have not been confirmed. Black holes might play a role too. Active supermassive black holes emit enormous amounts of light as they accrete matter. If early galaxies contained more active black holes than expected, their combined light could boost the galaxy's total luminosity. Some of the brightest early galaxies do show signs of black hole activity, though not all. The brightness problem also affects predictions about reionization, the process by which ultraviolet light from the first stars ionized the universe's hydrogen gas. If early galaxies were brighter, they produced more ultraviolet light, potentially completing reionization earlier than models predict. Observations of the cosmic microwave background suggest reionization ended around 400 million years after the Big Bang. Brighter galaxies would fit this timeline better. Another angle is dust. The models assume early galaxies contain little dust because dust forms from supernova ejecta, which takes time to accumulate. However, some James Webb observations show dust in galaxies less than 500 million years old. If dust formed faster than expected, it could affect the galaxy's brightness. Dust absorbs ultraviolet light and re-emits it as infrared, changing the spectral shape and potentially making galaxies appear brighter in certain wavelengths. The cosmological parameters themselves might be wrong. The models use values for dark matter density, dark energy strength, and the initial density fluctuations seeded by the Big Bang. If any of these values are incorrect, the predictions fail. Adjusting the parameters might bring the models into better agreement with observations, though this would have consequences for other predictions. Some scientists think the observations might be misinterpreted. The measured brightness could be artificially inflated by gravitational lensing or confusion with foreground objects. However, spectroscopy generally rules this out. The redshifts are real, and the galaxies are genuinely distant. The tension between models and observations is one of the biggest surprises from James Webb's first few years. It suggests our understanding of galaxy formation is incomplete. Something happened in the early universe that we have not accounted for. Some process made galaxies brighter, faster growing, and more numerous than we expected. Until we figure out what that process is, the puzzle remains unsolved. Light changes as it travels through expanding space. This is not a minor effect. It is the reason James Webb can see the early universe at all. Without expansion stretching light into infrared wavelengths, the most distant galaxies would remain invisible forever. When a galaxy emits light, that light has a specific wavelength determined by the atoms producing it. Hydrogen emits a bright line at 121 nanometers, deep in the ultraviolet. Oxygen emits lines in the visible range. These wavelengths are fixed by physics. They do not change based on the source. However, as light travels through space, the fabric of space itself expands. This expansion pulls on the light waves, stretching them to longer wavelengths. Ultraviolet light becomes visible light. Visible light becomes infrared. Infrared becomes far infrared. The farther the light travels, the more it gets stretched. Astronomers measure this stretching using redshift, denoted by the letter Z. A redshift of 1 means the light's wavelength has doubled. A redshift of 2 means it has tripled. MOME Z14, the most distant galaxy ever found, has a redshift of 14.44. Its light has been stretched by a factor of 15.44. Ultraviolet light that left at 120 nanometers arrives at Earth at 1,869 nanometers, deep in the infrared. This is why older telescopes could not find these galaxies. The Hubble Space Telescope operates primarily in visible and near-infrared wavelengths, covering roughly 400 to 1,600 nanometers. Galaxies with redshifts above 7 emit most of their light beyond Hubble's range. They are invisible to it. James Webb was designed specifically to solve this problem. Its instruments cover wavelengths from 600 nanometers to 28,000 nanometers, spanning visible red light through mid-infrared. This range captures light from galaxies at any redshift up to about 20. Beyond redshift 20, even James Webb struggles because the light shifts into wavelengths its detectors cannot see. The expansion of space is not like objects moving through space. It is space itself growing. Imagine dots on a balloon's surface. As you inflate the balloon, the dots move apart, not because they are traveling across the rubber, but because the rubber between them is expanding. Light traveling through expanding space experiences the same effect. The space between the light wave's peaks grows, stretching the wavelength. This expansion is accelerating. Dark energy drives the acceleration, pushing space to expand faster and faster. Galaxies far from us are receding at speeds that exceed the speed of light. This does not violate relativity because the galaxies are not moving through space faster than light. Space between us and them is growing faster than light can cross it. For the most distant galaxies, their light spent over 13 billion years traveling to us. During that time, the universe expanded significantly. Space that was much smaller when the light began its journey is now vastly larger. The light waves stretched along with that expansion, transforming into infrared radiation by the time they reach James Webb's mirrors. Understanding redshift allows astronomers to measure distances with precision. If you know a galaxy's redshift, you can calculate how far away it is and how long ago its light was emitted. This turns the telescope into a time machine. Higher redshift equals greater distance equals farther back in time. The most extreme redshifts James Webb has detected are around 14 to 15. These correspond to galaxies seen as they existed just a few 100 million years after the Big Bang. The light from these galaxies has traveled across 99% of the observable universe to reach us. It has been stretched by factors of 15 or more, shifting entirely out of the visible spectrum. Without this stretching, we could never see the early universe. The galaxies would emit ultraviolet light that Earth's atmosphere absorbs before it reaches the ground. Even space-based telescopes operating in ultraviolet could not see them because the distances are too great and the light too faint. Redshift transforms that ultraviolet light into infrared, a wavelength range where James Webb excels. The universe is revealing itself to us not in the light it originally emitted, but in the transformed, stretched, ancient radiation that has crossed billions of light years of expanding space. Every photon James Webb collects carries the signature of cosmic expansion imprinted on its wavelength. There is a galaxy where the black hole outweighs the stars, not by a small margin. The black hole's mass equals or exceeds the combined mass of every star in the galaxy. This should not be possible. Galaxies are supposed to dominate. Black holes are supposed to be minor components, residing at the center but contributing little to the total mass. CANUCSLRDZ86 breaks this rule. The galaxy's stars weigh a few 100 million times what our star weighs. The central black hole weighs at least that much, possibly more. The ratio is completely inverted from what we see in modern galaxies. It is as if the black hole formed first and the galaxy is an afterthought. This ratio is called the black hole to stellar mass ratio. In the Milky Way, the central black hole weighs about 4 million times what our star weighs. The galaxy's total stellar mass is around 60 billion times our star's mass. The ratio is roughly 1 to 15,000. The black hole is a tiny fraction of the total. In typical massive galaxies, the ratio is higher. The central black holes weigh more, sometimes reaching billions of solar masses. However, the galaxies also weigh more, maintaining a similar proportion. The heaviest black holes sit inside the heaviest galaxies. The relationship holds across billions of years of cosmic time. Except in the early universe, James Webb has found multiple galaxies where the black hole dominates. These little red dots consistently show black holes that are too massive for their hosts. The relationship between black hole mass and galaxy mass appears broken in the first billion years after the Big Bang. How did this happen? One theory suggests black holes formed from massive gas clouds that collapsed directly without forming stars first. These direct collapse black holes would start heavy, maybe thousands or tens of thousands of times our star's mass. Once formed, they would begin accreting matter rapidly, growing even larger. Meanwhile, the surrounding gas would form stars more slowly. The black hole gets a head start, and the galaxy never catches up. Another theory involves supermassive stars. If the first stars were hundreds or thousands of times heavier than typical stars, they would collapse into massive black holes when they died. These seed black holes would already be large, giving them an advantage in the race to accumulate mass. A third possibility is that star formation was suppressed near the black hole. As the black hole feeds, it emits intense radiation and powerful winds. This energy can heat and blow away nearby gas, preventing it from collapsing into stars. The black hole grows by eating the gas that would otherwise form stars, naturally leading to a high black hole to stellar mass ratio. The discovery of overmassive black holes has implications for understanding how modern quasars formed. Quasars are the brightest objects in the universe, powered by supermassive black holes weighing billions of times our star's mass. These quasars exist at redshifts as high as 7, meaning they formed when the universe was less than 1 billion years old. Growing black holes that large that quickly requires extreme feeding rates or massive seed black holes. If early galaxies routinely produced overmassive black holes, then the building blocks for quasars were in place very early. The little red dots that James Webb sees might be the progenitors of quasars, caught in an early phase of their evolution before the host galaxy has grown to match the black hole's mass. Over time, these systems likely evolved into more balanced configurations. The black hole's feedback eventually slows its own growth by heating and expelling nearby gas. Meanwhile, the galaxy continues accreting gas from larger distances, growing its stellar mass. Eventually, the black hole to stellar mass ratio decreases, approaching the values we see in modern galaxies. What this tells us is that galaxy and black hole growth are not always synchronized. In the early universe, black holes sometimes got ahead. They grew faster than their hosts, dominating the mass budget. This is opposite to what happens in the local universe, where galaxies grow first and black holes remain small. The universe's youth was a time of imbalance and extremes. Forces that later settled into equilibrium were still competing. Black holes had advantages they later lost, and the evidence is scattered across the sky in the form of galaxies where black holes rule and stars are an afterthought. For hundreds of millions of years after the Big Bang, the universe was dark, completely dark. No stars existed, no galaxies, just neutral hydrogen gas filling all of space, cooling as the universe expanded. This era is called the Cosmic Dark Ages, and it ended when the first stars ignited. That moment, when light flooded the cosmos for the first time, is called the Cosmic Dawn. It happened roughly 150 to 300 million years after the Big Bang. Gravity pulled gas into dense clumps, pressure built, temperatures rose, fusion ignited, and stars began to shine. The first stars were different from modern stars. They formed from pure hydrogen and helium with no heavier elements. This affects their structure and evolution. Without metals to facilitate cooling, the gas clouds could not fragment into small pieces. They collapsed into larger, more massive objects. The first stars were likely 50 to several hundred times heavier than our star. These massive stars burned incredibly hot and bright. They emitted huge amounts of ultraviolet radiation, far more than smaller stars produce. This radiation began to ionize the surrounding hydrogen gas. Neutral hydrogen atoms absorbed the ultraviolet photons, losing their electrons and becoming ionized plasma. A bubble of ionized gas formed around each star, growing larger as more photons streamed out. At first, these bubbles were isolated. Stars formed in scattered locations across the universe, each creating its own ionization zone. The regions between remained dark and neutral. Over time, more stars formed, more bubbles appeared. Eventually, the bubbles began to overlap, merging into larger ionized regions. This process is called reionization. It transformed the universe from a neutral gas-filled void into an ionized plasma. Reionization took hundreds of millions of years to complete. Early on, only small patches of space were ionized. By about 400 million years after the Big Bang, most of the universe had been reionized. The cosmic dawn transitioned into the cosmic noon, an era of intense star formation and galaxy growth. James Webb is observing galaxies from the cosmic dawn. These galaxies contain the descendants of the first stars. Some may still harbor a few population 3 stars, though most have already died. What we see in these galaxies is the early phase of structure formation, when the universe was just beginning to light up. The light from these galaxies is faint and redshifted. It has traveled across 13 billion light-years of expanding space to reach us. When the light left those galaxies, the universe was young and small. Now, it is old and vast. The light carries information about what conditions were like during the cosmic dawn, encoded in its spectrum and brightness. Observations of the cosmic dawn help answer fundamental questions. How quickly did the first stars form? How massive were they? How efficiently did they ionize the surrounding gas? These questions affect our understanding of everything that came after. The first stars set the stage for all subsequent cosmic evolution. Reionization also affected how later galaxies formed. Once the universe was ionized, small clumps of gas could not easily collapse to form stars. The ionized gas has higher pressure, resisting gravitational collapse. This suppressed star formation in low-mass halos, preventing the formation of very small galaxies. Only halos above a certain mass threshold could continue forming stars efficiently. This threshold explains why modern dwarf galaxies are less common than dark matter simulations predict. Dark matter halos of all sizes should exist, but only the larger ones can form visible galaxies in an ionized universe. The smallest halos remain dark, filled with gas that never cooled enough to form stars. The cosmic dawn was a turning point. Before it, the universe was simple, hydrogen, helium, dark matter, and radiation. After it, the universe became complex. Stars, galaxies, heavy elements, and the structures we see today. That transition happened in just a few 100 million years, a brief moment in cosmic history. James Webb is witnessing the aftermath of that transition. Every galaxy it sees from the first billion years carries echoes of the cosmic dawn. The light of the first stars, now long dead, shaped the galaxies we observe today. Their legacy is written in the distribution of elements, the structure of galaxies, and the ionization state of intergalactic gas. The universe went from darkness to light in the blink of a cosmic eye, and we are only now seeing the glow of that awakening, 13 billion years delayed by the time it took light to cross the universe. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies held together by gravity. The combined mass is enormous, weighing as much as a quadrillion stars. That mass warps space-time so severely that it bends light from background objects, creating a natural telescope. This effect is called strong gravitational lensing. Light from a distant galaxy passes through the curved space-time around a cluster. The curvature deflects the light, changing its path. From our perspective, the galaxy's image appears distorted, magnified, and sometimes multiplied. We see arcs, rings, and multiple copies of the same object. Astronomers use these natural telescopes to observe galaxies that would otherwise be invisible. The cluster's gravity acts like a lens, focusing light and boosting its brightness. Some galaxies get magnified by factors of 10, 20, even 50. Objects too faint for James Webb to detect on its own become visible thanks to the cluster's amplification. One famous lensing cluster is Abell 2744, also called Pandora's cluster. It sits about 3.5 billion light-years away and contains hundreds of galaxies. The cluster's mass distribution is complex because it formed from multiple smaller clusters that merged together. This complexity creates strong lensing effects across a wide area, making it an ideal target for deep surveys. James Webb has observed Abell 2744 extensively. The images reveal dozens of lensed galaxies, many from the early universe. Some appear as long arcs stretched across the cluster. Others show up as multiple images of the same galaxy scattered around different positions. By analyzing these images, astronomers can measure the cluster's mass distribution and determine the properties of the lensed galaxies. Another powerful lens is SMACS 0723, the target of James Webb's first deep field image. This cluster created numerous lensed arcs visible in the image. Some of the arcs correspond to galaxies at redshifts above 10, placing them in the first half-billion years after the Big Bang. Without the cluster's magnification, these galaxies would be too faint to see. The lensing effect depends on precise alignment. The background galaxy, the cluster, and the observer must be nearly in a straight line for strong lensing to occur. If the alignment is perfect, the result can be an Einstein ring, a complete circle of light surrounding the cluster. Most alignments are not perfect, producing partial arcs instead. Clusters also produce a phenomenon called weak lensing. This affects galaxies that are not perfectly aligned. Their images get slightly distorted, stretched in specific directions by the cluster's gravitational field. Individually, these distortions are subtle. However, by measuring the shapes of many background galaxies, astronomers can map the cluster's mass distribution, including the dark matter that makes up most of the cluster's mass. Gravitational lensing reveals dark matter's presence even though dark matter does not emit light. The lensing strength depends on total mass, visible and invisible. By comparing the lensing effect to the mass of visible galaxies, astronomers calculate how much dark matter is present. The answer is usually 5 to 6 times more dark matter than regular matter. Some clusters create extremely rare events called superlensing. This happens when multiple clusters align along the same line of sight, each contributing to the lensing effect. The combined magnification can reach factors of 100 or more. These events are so rare that only a handful are known, but they allow James Webb to see galaxies from even earlier in cosmic history. The downside of gravitational lensing is that it distorts the galaxy's shape. To study the galaxy's true structure, astronomers must model the lensing effect and reverse it. This requires detailed knowledge of the cluster's mass distribution. Teams create sophisticated models that account for the positions and masses of individual cluster galaxies, as well as the dark matter halos surrounding them. Nature provided these cosmic magnifying glasses scattered throughout the universe. They are not placed randomly. Clusters form at nodes in the cosmic web where dark matter filaments intersect. These locations concentrate mass, creating the strong gravitational fields needed for lensing. By targeting clusters, James Webb maximizes its ability to see the early universe. Every major lensing cluster has been observed by James Webb, Abell 2744, SMACS 0723, MAX 0416, and dozens of others. Each observation reveals new lensed galaxies, pushing the observational frontier farther back in time. The clusters are doing work that no telescope alone could accomplish, bringing the universe's earliest structures into view. The light we see from early galaxies shows us stars that no longer exist. Those stars burned, fused, and exploded billions of years ago. What remains is their ancient light, photons that have been traveling through space for over 13 billion years. Each photon carries information about the star that emitted it. When a star forms, it creates a specific pattern of light. Hot, young stars emit mostly ultraviolet and blue light. Cooler, older stars emit red and infrared light. By analyzing the spectrum, astronomers can determine the star's temperature, age, and chemical composition. This works even when the star is billions of light years away. James Webb spectrographs split light into its component wavelengths, creating detailed spectra. These spectra show emission lines from hydrogen, helium, oxygen, carbon, and other elements. Each element leaves a unique fingerprint. The pattern of lines reveals what the galaxy is made of and how its stars are evolving. Early galaxies show strong hydrogen and helium lines, consistent with stars forming from primordial gas. Some also show carbon and oxygen lines, indicating that at least one generation of stars has already died and enriched the gas. The presence of these heavier elements tells us how many stellar generations have passed since the galaxy formed. Star formation is an ongoing process. Gas clouds collapse, fragment into smaller pieces, and ignite as new stars. This happens continuously in active galaxies. The stars we see in James Webb images are not the original stars that formed. They are later generations, built from gas enriched by earlier supernovas. Each generation adds more heavy elements. The first generation, population 3 stars, produced carbon, oxygen, and some nitrogen. When they exploded, these elements mixed into the surrounding gas. The second generation formed from this enriched material, fusing those elements into heavier ones like silicon and iron. The third generation incorporated even more metals. By the time we see a galaxy at redshift 10, it has already gone through multiple cycles. The stars currently shining are not pristine. They contain metals forged in earlier stars. The amount of metal reveals how many cycles have occurred. High metallicity means many generations. Low metallicity means the galaxy is still young. The light from these stars left the galaxy when the universe was less than 500 million years old. It traveled through expanding space for 13.3 billion years. During that journey, the light got stretched from ultraviolet into infrared. The stars emitting it have long since died. Some exploded as supernovas. Others quietly faded into white dwarfs. A few collapsed into black holes. What we observe is a snapshot of the past, the galaxy frozen in time at an early stage of its evolution. We cannot see what happened to it afterward. The galaxy today, if it still exists, is likely much larger and older. It may have merged with other galaxies, transforming into something completely different, but we will never see that future state because the light showing it has not reached us yet. This delay creates a strange situation. We can observe galaxies at multiple stages of their lives by looking at different distances. Nearby galaxies show us what evolved systems look like today. Distant galaxies show us what young systems looked like billions of years ago. By combining observations across distances, astronomers build a timeline of galaxy evolution. The stars forming in early galaxies are the ancestors of stars that exist today. The gas that formed them eventually became part of later galaxies through mergers and accretion. Some of that gas might have ended up in the Milky Way. Some might have formed our star and the planets around it. The atoms in your body were forged in stars that lived and died billions of years ago. James Webb sees the light from those ancient stars, photons that escaped just after the cosmic dawn. Each photon is a messenger from the past, carrying news of events that happened when the universe was young. The stars are gone, the galaxies have changed. What remains is the light, traveling eternally through the void until it finally arrives at a telescope mirror. Black holes have a growth problem. They cannot eat faster than a certain rate without choking themselves. The limit is called the Eddington limit, and it depends on radiation pressure. As matter falls into a black hole, it heats up and emits light. That light pushes outward, counteracting gravity. If the light is strong enough, it blows away incoming matter, limiting how fast the black hole can grow. The math is straightforward. A black hole weighing 1 million times our star's mass can grow by about 1% every million years at the Eddington limit. To reach 1 billion times our star's mass, starting from 100 solar mass seed, takes over 700 million years of continuous feeding at maximum rate. This is barely enough time if the black hole forms immediately after the Big Bang and feeds non-stop. Yet, James Webb finds black holes weighing hundreds of millions or billions of solar masses at redshifts above 7. These black holes existed when the universe was less than 700 million years old. The timeline is too short. Even feeding at the maximum theoretical rate, starting from stellar mass seeds, they should not be that large yet. This suggests either the seeds were larger than expected or the growth rate exceeded the Eddington limit. Both possibilities challenge standard models. Large seed black holes require special formation mechanisms like direct collapse or supermassive stars. Super Eddington accretion requires conditions that overcome radiation pressure. Some models propose that black holes formed from collapsing gas clouds rather than dying stars. If a massive cloud of gas, weighing tens of thousands of times our star's mass, collapsed directly into a black hole without forming stars first, it would create a heavy seed. This gives the black hole a significant head start. Growing from 10,000 solar masses to 1 billion takes much less time than growing from 100. Direct collapse requires specific conditions. The gas must be metal-free because metals help gas cool, allowing it to fragment into stars before collapsing completely. The gas must also be exposed to a strong radiation field that prevents hydrogen molecules from forming. Without molecules, the gas cannot cool efficiently, forcing it to collapse into a single massive object. These conditions might have been common in the early universe. The first stars produced intense ultraviolet radiation that kept nearby gas clouds hot. As these clouds collapsed, they could form direct collapse black holes. If this happened frequently, the universe would have many heavy seed black holes ready to grow into supermassive giants. Alternatively, supermassive stars could have formed. These stars would weigh hundreds or thousands of times our star's mass. They would burn through their fuel in a few million years and collapse into massive black holes. These seed black holes would already weigh thousands of solar masses, again providing a head start. The problem with both theories is that we have no direct evidence for either. Direct collapse black holes and supermassive stars are theoretical. James Webb has not found definitive examples of either. Until we observe them forming or identify their signatures in early galaxies, they remain speculative solutions. Super Eddington accretion is more plausible because we have observed it in at least one case. LID 568 feeds at over 40 times the Eddington limit. If such episodes were common in the early universe, black holes could grow much faster than standard models allow. A few million years of Super Eddington feeding could add as much mass as tens of millions of years at normal rates. The catch is that Super Eddington episodes are likely short-lived. The black hole rapidly consumes nearby gas, and without a continuous supply, the feeding rate drops. For this to solve the growth problem, the universe must deliver gas to black holes efficiently and frequently. Mergers between gas-rich galaxies might provide this delivery mechanism, triggering bursts of rapid accretion. Another angle is that black holes grew during the cosmic dark ages, before the first stars formed. If primordial black holes existed shortly after the Big Bang, they would have had extra time to grow. A black hole forming 1 million years after the Big Bang gains an additional 150 million years of growth time compared to one forming after the first stars ignited. Primordial black holes are controversial. They require specific conditions during the Big Bang to form, and most models do not produce them in large numbers. However, if they exist, they elegantly solve the growth problem by giving black holes more time. The discovery of overmassive black holes is forcing theorists to revisit assumptions. Something about the early universe enabled rapid black hole growth. Either the seeds were heavier, the feeding rates were higher, or the timelines were longer than we thought. Each possibility requires rethinking fundamental aspects of how black holes form and evolve. James Webb's first deep field image is not just a picture, it is a timeline. The image shows galaxies from multiple eras, each visible at a different distance. Nearby galaxies appear as they looked a few billion years ago. The farthest galaxies appear as they existed over 13 billion years ago. The entire history of the universe is compressed into one frame. The image required 12.5 hours of observation time. James Webb stared at galaxy cluster SMACS 0723, collecting photons one by one. The longer the exposure, the more faint light accumulated. Galaxies too dim to detect in short exposures became visible after hours of integration. The depth of the image is measured by magnitude. Astronomers use a logarithmic scale where each 5 magnitudes represents a factor of 100 in brightness. The faintest objects in the SMACS 0723 image reach magnitude 31 in infrared wavelengths. That is 100 million times fainter than the faintest stars visible to the naked eye under perfect conditions. At these extreme depths, almost every speck of light is a galaxy. Stars are too faint to see at these distances. What appears as tiny dots or smudges are entire galaxies containing billions of stars. The number of galaxies in the image approaches 10,000. Each one is a complete world, separated from us by unfathomable distances. The image shows structural diversity: spiral galaxies with defined arms, elliptical galaxies that are smooth and featureless, irregular galaxies with chaotic shapes, merging galaxies caught in the act of collision. Every morphological type is represented, demonstrating the variety of paths galaxies can take during their evolution. Color in the image corresponds to wavelength. Blue represents shorter infrared wavelengths. Red represents longer wavelengths. The color of each galaxy reveals its distance. Nearby galaxies appear blue because their light has not been stretched much. Distant galaxies appear red because their light has been redshifted significantly. The reddest objects are the farthest, dating back to when the universe was less than 1 billion years old. Some galaxies appear multiple times due to gravitational lensing. The cluster's mass bends light from background galaxies, creating multiple images. These duplicates are visible as arcs or distorted shapes around the cluster's center. By measuring the separation between images, Astronomers calculate the cluster's mass, including its dark matter content. The image also captures galaxies in the cluster itself. These are the bright, large galaxies near the image center. They sit about 4 billion light-years away, much closer than the background galaxies. The cluster formed from mergers of smaller galaxy groups over billions of years. Its current state represents a mature, massive structure. Between the cluster and the most distant galaxies lie intermediate distance objects. These galaxies existed at various times between 4 billion and 12 billion years ago. They show what galaxies looked like during different evolutionary phases. Some are actively forming stars. Others have finished star formation and are fading. The diversity illustrates how galaxy populations change over time. What makes this image historically significant is that it surpassed all previous deep fields in both depth and coverage. Hubble's deepest images required weeks of observation time and covered smaller areas. James Webb achieved comparable depth in hours, opening the possibility of mapping larger regions of sky to similar sensitivity. The scientific value lies in the statistics. With thousands of galaxies visible, astronomers can measure how galaxy properties change with distance and time. They can count how many galaxies existed at different epochs. They can study the distribution of galaxy types and how it evolved. These measurements constrain models of galaxy formation and test cosmological theories. Every galaxy in the image has a story that will never be fully told. We see them at one moment in their history, frozen by the time it takes light to travel. We do not know what happened before or after. We cannot follow their evolution in real time. All we have is this snapshot, a single frame from a cosmic movie spanning billions of years. The deep field reminds us of our place in the universe. We are observers on one small planet, looking out at structures so vast we can barely comprehend them. The light from these galaxies has traveled longer than our species has existed. It began its journey when the universe was young, and it arrives now to be captured by sensors made of atoms forged in ancient stars. Every few months, James Webb breaks its own distance record. A galaxy is found at redshift 13, then 14, then 14.44. Each discovery pushes our view deeper into the past, closer to the Big Bang itself. The progression seems relentless, as if there is no limit to how far back we can see. Redshift measures how much light has been stretched by cosmic expansion. Higher redshift means greater distance and earlier time. A redshift of 1 corresponds to looking back about 7.7 billion years. Redshift 6 corresponds to 12.7 billion years ago, when the universe was only about 800 million years old. Redshift 14 corresponds to 280 million years after the Big Bang. Each increment in redshift becomes harder to achieve. Going from redshift 0 to 1 is relatively easy. Many galaxies exist at that distance. Going from 13 to 14 is difficult. Galaxies are rare at those distances, and their light is extremely faint. Finding them requires surveying large areas of sky or staring at small regions for extended periods. The current record holder is MOMZ-14 at redshift 14.44. This galaxy was not the first candidate discovered at high redshift. Several other objects showed similar colors, suggesting extreme distance. However, MOMZ-14 was the first to have its redshift confirmed spectroscopically. Without spectroscopy, redshift estimates are uncertain. An object that appears distant based on its color could be a closer galaxy with unusual properties. Spectroscopic confirmation requires detecting emission or absorption lines in the galaxy's spectrum. These lines correspond to specific elements and have known wavelengths. By measuring where these lines appear in the observed spectrum, astronomers calculate how much the light has been redshifted. This gives a precise distance measurement. James Webb's near-infrared spectrograph is designed for this task. It can observe faint galaxies and extract spectra, even when the objects are barely visible. The instrument splits light into hundreds of individual wavelength channels, creating a detailed spectrum showing exactly where emission lines appear. Before James Webb, The highest confirmed redshift was around 11 to 13, achieved by Hubble and ground-based telescopes. These galaxies existed about 400 million years after the Big Bang. James Webb has extended the record by roughly 100 million years, reaching back to 280 million years post-Big Bang. Is there a limit to how far we can see? Theoretically, yes. The earliest galaxies must have formed sometime after the first stars ignited, which happened around 150 to 200 million years after the Big Bang. Before that, there were no stars, so no galaxies. James Webb is approaching this limit. Another factor of 2 in distance would put us at the earliest possible galaxies. However, finding those earliest galaxies is challenging. The universe was smaller and denser back then, meaning galaxies were likely smaller and fainter than the ones we have found so far. Detecting them requires longer exposure times and larger survey areas. The Nancy Grace Roman Space Telescope, launching in 2027, will help by surveying much larger areas of sky than James Webb can. Each record-breaking discovery generates excitement and questions. How did galaxies form so quickly? Why are they brighter than expected? What processes enabled rapid star formation in the early universe? Every new galaxy provides data to test theories and refine models. The chase for higher redshifts is not just about records, it is about understanding the universe's infancy. The first galaxies seeded all subsequent structure. They produced the first heavy elements. They ionized the universe. They set the stage for everything that came after. Observing them directly answers fundamental questions about cosmic origins. James Webb will likely continue breaking its own records for years. As more survey data becomes available, astronomers will identify even more distant candidates. Spectroscopic follow-up will confirm or rule out each one. The redshift record will inch upward, approaching the theoretical limit. Eventually, we will reach a point where galaxies simply do not exist farther back. We will be looking at the cosmic dawn itself, the moment when the first stars ignited and light flooded the universe for the first time. That moment is within reach now, just beyond the current observational frontier. James Webb has revealed a universe more complex and dynamic than anyone predicted. Galaxies forming faster, black holes growing larger, structures appearing earlier. Every discovery challenges our models and expands our understanding of cosmic history. What does all this mean for us, for humanity, for our place in this impossibly vast universe? First, it means we are younger than we thought, not individually, but collectively, as a species connected to the cosmos. The atoms in our bodies were forged in stars that lived and died billions of years ago. Those stars formed in galaxies like the ones James Webb observes. The iron in our blood came from supernovas. The carbon in our DNA came from stellar nucleosynthesis. We are made of stardust, literally composed of elements created in the early universe. The discoveries also reveal how special our moment in time is. We live 13.8 billion years after the Big Bang, in a universe that has matured and evolved. The chaotic, violent early universe is long gone. Star formation has slowed. Galaxy mergers have decreased. The universe today is calmer, more structured, more hospitable to life. If we existed during the cosmic dawn, conditions would have been far more extreme. Second, the discoveries emphasize scale. The universe contains trillions of galaxies. Each galaxy contains billions or trillions of stars. Many of those stars have planets. The number of potentially habitable worlds exceeds comprehension. If even a tiny fraction of those worlds develop life, the universe could be teeming with it. We are not special in terms of location or uniqueness. We are one planet among countless others. Yet, we are also unique in our ability to observe and understand the cosmos. No other species on Earth has built telescopes or developed physics. No other known life has deciphered the universe's history or measured its age. Intelligence capable of scientific discovery may be common in the universe, or it may be incredibly rare. We do not know. What we do know is that we have it, and we are using it to explore our origins. Third, the discoveries reveal how much we still do not understand. Dark matter makes up most of the universe's mass, and we have no idea what it is. Dark energy drives cosmic expansion, and we do not know its nature. The Hubble tension suggests our cosmological model is incomplete. Supermassive black holes grow faster than models predict. Galaxies form earlier and brighter than simulations allow. Every answer raises new questions. This is the nature of science. We build models to explain observations. New observations challenge those models. We revise the models, making them more accurate. Then new observations challenge the revised models. The process repeats endlessly. We asymptotically approach truth without ever fully reaching it. Each generation of scientists gets closer, but there is always more to learn. Fourth, the discoveries remind us of our cosmic insignificance. We live on a tiny planet, orbiting an average star in an ordinary galaxy in an unexceptional part of the universe. Our galaxy is one of trillions. Our star is one of hundreds of billions in that galaxy. Earth is one of potentially billions of habitable planets just in the Milky Way. The scale dwarfs us. Yet this insignificance is also liberating. The universe does not revolve around humanity. Cosmic events unfold according to physical laws that do not care about us. Black holes merge. Galaxies collide. Stars explode. These processes happened long before humans existed and will continue long after we are gone. We are observers, witnesses to a grand drama that transcends our existence. Finally, the discoveries inspire wonder. Looking at James Webb images, seeing galaxies billions of light years away, recognizing that we are viewing the universe as it existed in its youth. This provokes a sense of awe that transcends scientific knowledge. It touches something deeper, a recognition of beauty and mystery that goes beyond equations and data. The universe is incomprehensibly large. It is incomprehensibly old. It operates on scales of time and distance that our minds struggle to grasp. Yet we have reached out with our instruments and our intellect, peering across billions of light years to witness the cosmos in its infancy. We have decoded the light from ancient galaxies. We have measured the masses of black holes that formed before Earth existed. We have traced the history of the universe from the Big Bang to the present. This is humanity's greatest achievement, not the construction of cities or the invention of technology, but the understanding of our place in the cosmos. We are small, we are brief, we are insignificant, and yet we are capable of comprehending the universe itself. That paradox defines our existence. We are the universe become conscious of itself, matter organized in a way that allows it to study matter, atoms contemplating atoms. James Webb has shown us a universe stranger and more magnificent than we imagined. It has raised questions we do not yet know how to answer. It has revealed structures we do not yet understand. And it has reminded us that despite our smallness, we have the capacity to explore, to discover, and to wonder at the impossible vastness of everything that exists.